This is a crash course in logic. Now hopefully you already downloaded your notes. Logic is the science of reasoning, and this kind of logic that we're studying is two-valued logic. In other words, every statement only has two values. It's either true or false. The building blocks of logic are things called statements. Okay, so statements, the kinds that we're going to work with would be like simple things like, oh, x equals 2. X is greater than 2. X is less than or equal to 2. Okay, some other more difficult statements are what we call universal statements and existential statements. Okay, a universal statement looks something like this. For all real numbers x and y, comma, x plus y squared is equal to x squared plus 2xy plus y squared. This is called a universal statement, because if you just look at the first two words, right? And you can see that this is true. This is a true statement. An example of an existential statement would be there exist integers a and b such that pi equals a over b. And again, it's existential because if you just look at the first two words, right? There exist. Another word for there exists would be sum, right? Because in mathematics, sum means at least one. And we can clearly see that this statement is false because pi is an irrational number. You cannot write it as a ratio of two integers. Now, in mathematics, we like to symbolize. We don't like to write out all these words. So the symbolization for the first universal statement would be this. So this symbol is for all. X is an element of the real numbers, comma. X plus y squared is equal to x squared plus 2xy plus y squared. That's how we symbolize it. So you got to get used to these symbols. For all real numbers x, comma, this. And then for the existential statement, it looks like this. There exist integers a and b. Oh, x and y. Oh boy, x and y are real numbers. So there exist integers a and b. So a and b are elements of the integers, which is capital Z, such that, that's a symbol for such that, pi equals a over b. And that's how we symbolize. So I believe in your notes, I think I have all the different sets you need to know, like the real numbers, the integers, the complex numbers, the whole numbers, the natural numbers, and so forth. Okay, now, first thing, how do you negate a statement? Well, if you have a simple statement like this, it's easy to negate, okay? Now, usually in logic, the first statement we usually label P. Okay, so you have P, and then the negation of statement P looks like this. That's the negation of statement P, or we simply say not P. So let's do some examples. Ah, darn it, I've got to erase it. Okay, so let's say we have P, and then let's make a kind of a chart here. Let's see, how can I do this? Not P. So let's say we have a simple statement like x equals 2. How would you write the negation of that statement? Well, very simple. X is not equal to 2, right? What about x is greater than 2? What would be the negation of that? X is less than or equal to 2, right? All the numbers that are not greater than 2. What about x is less than or equal to 2? What would be the negation of that? Well, simple. X is greater than 2. So when you have a simple statement, it's very easy to negate it, okay? But how do you negate a universal or an existential statement? Okay, so suppose statement P is, okay, let's do another. For all real numbers x and y, comma, x plus y quantity cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. We know this is a true statement, right? So how do you write the negation? Well, anytime you have a universal statement, the negation is going to be an existential statement. So it's going to be there exist real numbers x and y such that x plus y quantity cubed is not equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And that's how you negate a universal statement. In fact, every universal statement has this form. Okay, so here, let's say statement Q is a universal statement. For all box, comma, triangle. Right? If you look at the form, it always looks like that. So if you want to negate it, it's always going to be there exists box such that not triangle. So it really doesn't matter what kind of statements you have in there, the form is always going to be the same. And you can probably guess then, so like what if you had statement R, which is an existential statement. There exists box such that triangle. To negate it, all you have to do is write a universal statement. For all box, comma, not triangle. So it's probably easier just to memorize the forms instead of looking at the words. And in fact, right there, that's the beauty of symbolic logic. We don't have to rely on the meaning of the words. So another example then. So how would you negate, okay, let's say statement S is there exist integers a and b such that radical 2 is equal to a over b. And again, we know this is a false statement because radical 2 is an irrational number. But how do you negate it? What is the negation of statement S? It's going to be a universal statement. For all integers a and b, comma, so if this is the triangle, you got to negate it. So root 2 is not equal to a over b. It's quite simple. Okay, so what we did here is we learned how to negate statements. Okay, next, truth tables. Now there are 5 basic truth tables that you need to know in logic. Okay, so let's start. Now the first one you kind of already know. Now when you have a single statement P, remember every statement is either true or false. There's no in between, right? So when you negate that statement, not P, if statement P is true, then the negation of it got to be false, right? And if a statement is false, its negation has to be true. This is called a truth table, which shows you all the different possibilities of a statement. So when you have a single statement, it's quite simple. Okay, but now what happens when you have 2 statements? What happens when you have statements P and Q? There are 4 possibilities. And this is the standard way of showing all 4 possibilities. So P will always be true, true, false, false. And Q will always be true, false, true, false. That's just the standard way of doing things. So the first statement is called disjunction. So this symbol here means the disjunction of P and Q, or we simply say P or Q. So most commonly this symbol means or. Now the or statement is true when at least one of the 2 components is true. So here's P and Q. Is at least one of them true? Yes, so it's true. Is at least one of them true? Yes, so it's true. Is at least one of them true? Yes, so it's true. Is at least one of them true? No, so it's false. The or statement is true when at least one of the components is true. Now that you have or, you can probably guess, you got and. This is called conjunction. The conjunction of P and Q, or we simply say P and Q. The and statement is true when both components are true. So here are the 2 components. Are both of them true? Yes, so it's true. Are both of them true? No, so it's false. Are both of them true? No, so it's false. Are both of them true? No, so it's false. Now ultimately what you want to do is you want to just memorize these truth tables, right? So you think, okay, or is going to be true, 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 false, and is going to be true, false, false, false. So at the beginning of logic, what you try to do is just try to memorize the forms, and then you can kind of see, and then later on when it solidifies in your mind, then you can kind of see how it fits in with regular math, as you will see later. Okay, the next one is this. This is called the conditional statement. Or, if P, then Q. So, when you see this, this means if P, then Q. Normally you see conditional statements when you read theorems, like especially in geometry, yeah? Another way to say this would be P implies Q. Now if you look at your notes, there's a whole bunch of ways that you can say this, right? So if P then Q, P implies Q, Q if P, P only if Q, P is a sufficient condition for Q, Q is a necessary condition for P. All of those things mean the same thing. It means if P then Q. So you gotta go through those notes and memorize all those things. Now when you have a conditional statement, okay, let me show you. You have a conditional statement, which is if P then Q, you can form these other statements. First one, the converse. I think you guys learned this in geometry. The converse of P implies Q is Q implies P. You can also perform the inverse. So the inverse of P implies Q would be not P implies not Q. And the most important one, as you will see, is the contrapositive. The contrapositive of P implies Q is not Q implies not P. And we're going to see why that's going to be the most important one later. Anyway, what is the truth table for P implies Q? Well, the only time a conditional statement is false is when the first part is true and the second one is false. That's the only time it's false. All other cases it's true. So one way to think about it is, okay, suppose I make this statement. If you do your homework, then I will pay you $5. So what would happen if you did your homework and then I paid you $5? Am I a liar? No, right? Both parts are true. But what if you did your homework and I didn't pay you $5? Am I a liar? Yes, I'm a liar, so that's why it's false. What if you didn't do your homework and then I paid you $5? Am I a liar? No, I'm stupid, but I'm not a liar. What if you didn't do your homework and then I didn't pay you $5? Am I a liar? No. So that kind of helps you kind of understand how this works. But ultimately, like I said, you're just going to memorize. The only time a conditional statement is false is when the first one is true and the second one is false. All other cases, it's true. Okay, and then the last statement that you have to memorize is the biconditional. See how, notice how the arrows go both directions? The biconditional statement actually means if P then Q and if Q then P. That means you can go both directions. And this is how the truth table looks for the biconditional statement. These are all in your notes, by the way. And notice that, look, the biconditional statement is true when the two components are the same, either both true or both false. The biconditional statement is false when they're different. The two components are different. So these are the basic truth tables that you need to know. And then you have to be able to form truth tables for other larger statements. So let me give you an example of that. Just one example should be enough. Construct the truth table for the statement P if and only if not Q and not P or Q. Try to include as many as I can. No! Let's do not P implies Q. Yeah. So here's a more complicated statement. Construct the truth table for this. So now remembering, now if you want to, you can make what we call training wheels. Here's P and here's Q. Now remember, P is always true, true, false, false. This is the standard way of doing it. And Q is always going to be true, false, true, false. This shows all four possibilities when you have two statements. Okay, so here we go. P is, we know, is true, true, false, false. Now if Q is true, false, true, false, not Q is going to be false, true, false, true. You can kind of think of the negation sign as negative, right? But see, the thing is, numbers are negative, like you can have -7, but when you have statements, statements aren't negative, they have negations. Yeah? So it's kind of like the same concept, but numbers have a certain sign. It kind of reminds you of a negative sign, yeah? Anyway, These two statements are put together with biconditional. So when is the biconditional true? When both of them are the same and they're different and it's false when they're different. So they're different, so it's false. They're the same, so it's true. They're the same, so it's true. They're different, so it's false. So this column here represents this statement there. Now we have to do this one. See how, notice the parentheses, the order. So we do what's in the parentheses first. So P is true, true, false, false. Not P is going to be false, false, true, true. Q is true, false, true, false. And then I'm going to have to put these two statements together with the conditional statement. Now remember, the only time a conditional statement is false is when the first one is true and the second one is false, right here. All other cases it's true. So right there, this column represents this statement. Then I have to put these two statements together with and. And when is the and statement true? When both components are true. So are both components true? No, so it's false. Are both components true? Yes. Are both components true? Yes. Are both components true? No. So this column here represents this entire statement there. And all a truth table does is it just shows all the different possibilities that this statement can have. In other words, if you have two statements, if the first one is true and the second one is false, if P is Q and then P is true, Q is false, then this statement here is true. It just shows you all the different possibilities. But we can do a lot of good things with truth tables. If I were to make two truth tables and they came out to the same thing, okay, let's do one. Let's do another one. Okay, here's P and Q. Construct the truth table for, I'll put the training wheels on for you. True, false, true, false. Construct the truth table for not P or Q. Now, some of these are so easy you can just do it in your head, right? Because we know P or Q is what? What is P or Q? True, 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 false. So if you negate it, you're going to get false, 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 true. Okay, now construct the truth table for not P and not Q. Okay, well if P is true, true, false, false, not P is going to be false, false, true, true. If Q is true, false, not Q is going to be false, true, true. And then I have to put these two together with and. The and statement is true when both of them are true, right? Are both of them true? No. Are both of them true? No. Are both of them true? No. Are both of them true? Yes. Now, I want you to notice something about this. Here's the truth table for this statement. Here's the truth table for this statement. What do you notice? They're exactly the same. When two statements have exactly the same truth table, we say that these statements are logically equivalent. And this is how we write it. So the negation of P or Q is logically equivalent to not P and not Q. Logically equivalent means they have the same truth table. Now, notice that it kind of looks like an equal sign. Yeah, and it has the same concept of equal, except numbers are equal, but statements are logically equivalent. So it's kind of like the same symbol, but not really. Just like negation, it means negative, right? But only numbers can be negative, but statements, they're negations, right? Now, in your notes, there's a list of logically equivalent statements that you must memorize. Okay, this is one of them. Doesn't this remind you of the distributive property? Yeah, so you can distribute a negation sign to an or statement, but what happens? The or changes to and. And you could probably guess that the negation of P and Q would be not P or not Q. So you can distribute a negation sign to an and statement, but then the and changes to or. These are called De Morgan's laws. You don't have to know the name, but you just got to know how to use them. Now there are some very important equivalences, like I said, that are in your notes, and here's one. This is probably the most important one. P implies Q is logically equivalent to not Q implies not P. What? That means any conditional statement is logically equivalent to its contrapositive. So the contrapositive of a conditional statement means exactly the same thing as a conditional statement. Super important. Another one is P implies Q is logically equivalent to not P or Q. So a conditional statement is also logically equivalent to an or statement. Or vice versa. An or statement is logically equivalent to a conditional statement. All you have to do is negate the first one and leave the second one alone. I would say these are the four most important ones that you have to know for logic. But there's some other ones that are in your notes, so you need to know those as well. Now, if you don't believe me on these, all you got to do is make truth tables, and then you will see that they're exactly the same. In fact, if somebody were to ask you to prove that statements are logically equivalent, that's what you would do. You make a truth table for this, you make a truth table for that, and show that they come out exactly the same. Now, what would happen if you had, now I don't think you're going to get this, but what if you had three statements, P, Q, and R? How do you make a truth table for that? Well, how many possibilities are there going to be when you have 8 statements? Well, if each statement is true or false, you have 2 possibilities. 2 times 2 times 2 is 8. There's 8 possibilities. This is the standard way of doing it. P is going to be true, 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 and false, 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 false. Q is going to be true, true, false, false, true, true, false, false. And then R will be true, false, true, false, true, false, true, false. And even if we had more statements, like 4 or 5 or whatever, it follows the same pattern. The one that's always on the furthest right is always going to alternate by 1s, right? True, false, true, false, true, false, true, false. The next one in alternates by 2s. The next one in alternates by 4s, and so forth and so forth. But I don't think you're going to get that. But this is just to let you know. Okay, next thing. Deducing arguments. Okay, what is an argument? An argument looks like this. This is the most famous argument in logic. If P, then Q. P, therefore Q. So P implies Q. If you do your homework, then I will pay you $5. You do your homework, what can you conclude from that? That you're going to get $5, right? This is called a valid argument. Now, what is a valid argument? A valid argument is when the 2 premises are true. These are called premises. If these 2 statements are true, then that statement will be true as well. This is called the conclusion. The premises, the conclusion. So in any argument, if the premises are true, and then the conclusion is always going to be true, we call that a valid argument. Now, this is a valid argument. Again, it's the most famous argument in logic. We call this one modus ponens. I don't think you have to know the name, but you have to know the form. The next most famous argument in logic is this. P implies Q, Q implies R. Therefore, P implies R. This is called the Law of Syllogism. Oh, okay, now, using these 2 valid arguments, now we can deduce logical conclusions if we're given some premises. So, this is a skill that you need to get under your belt. So, let's start out easy. P implies Q, Q implies R, P, now let's kick it up a notch. R implies S, P, therefore what? So, if these 4 premises are true, what is a valid conclusion? I mean, what's a logical conclusion? What logical conclusion can I deduce? Well, based on these 3 statements here, P implies Q, Q implies R, R implies S, what can you conclude from that? P implies S, right? From the Law of Syllogism. But P implies S, P, therefore, S, modus ponens. That's easy. Okay, you ready to kick it up a notch? Here we go. P implies Q, not Q, therefore what? What is a logical conclusion if you assume these to be true? Well, what did we learn? Any conditional statement is logically equivalent to its contrapositive. So what's the contrapositive of P implies Q? Not Q implies not P. So doesn't this have the form of modus ponens? Gorilla implies banana. Gorilla, therefore banana. It's very simple. So, see, that's the beauty of symbolic logic. See, no matter what words they give you, if you just symbolize it, then we look at the form. So we don't really have to rely on the meaning of the words anymore. We just look at the form of the argument. Okay, let's do another one. P or Q, not P, therefore what? What can I conclude from that? Well, what did we learn? Any or statement is logically equivalent to a conditional statement, right? And how do you do that? You negate the first and leave the second one alone. Now, once you do that, look how easy this is. Gorilla implies banana. Gorilla, therefore banana. Modus ponens. Ah. Oh, so Mr. Park, knowing all of these logically equivalent things, that's like really important. Duh. Okay, let's do a more complicated one. So, when you're doing your worksheets and you have an argument and there's a lot of words, what you do is you symbolize. So like each phrase you assign a letter and you write it like this, and then once you just symbolize it, it should be quite easy. Okay, let's kick it up a notch. Not P or not Q. Okay, wait, let me start over. Not P and Q. Not P and Q. P, therefore what? Okay, this is still kind of simple. Okay, well, what do I do with this? Well, what did we learn? Can I distribute a negation sign? Yes, De Morgan's law. Not P or not Q. So you can distribute a negation sign, but you got to change the and to or the or to and, right? And then you can change an or statement to a conditional statement by negating the first and then leaving the second alone, right? And then now look how easy this is. This is modus ponens. Gorilla implies banana. Gorilla, therefore banana. Now, when you have a biconditional statement, something like this. P if and only if Q, let's say Q, no, moose breath. P implies Q, P if and only if Q, P implies not R, Q, therefore what? Now when you have a biconditional statement, you can remember what it means. It means P implies Q and Q implies P. So you can use it in either direction. So you use it in the direction that's going to be helpful to you now. Which one is that? In this case, it's going to be, you want to use it as Q implies P. Because look, Q implies P, P implies not R. What can I conclude from those two statements, from these two? Q implies not R, right? That's Law of Syllogism. So I have Q implies not R, Q, therefore, not R, modus ponens. So the key is, see, when you just have a single statement, okay, fine, but all the other statements in there, you want to change them to conditional statements so you can link them up with the Law of Syllogism. So if you see things like this, what you want to do is change it to a conditional statement. Okay, so that's a crash course in logic right there. Hopefully that will be enough so that you can do most of your worksheets. Now, some of the other problems, so this is like the nuts and bolts of logic, but then you also have logic puzzles, yeah? So I think a lot of you have experience with that. So the kinds of problems you're going to get are either going to be like this, symbolic logic or logic puzzles. And if you have difficulty with logic puzzles, then come see me, and then hopefully this helps.